I think now it's should be recorded. I use the Google Hot Air.
Okay.
Yeah.
Can you turn on your camera and point it at the audience so I can see them?
Yeah, I plug in the audio already.
What?
The audio is
No,
the audio
not audio. I'm talking about turning on your camera and pointing it at the audience. How's the sound?
Sound okay. Sounds okay.
Okay.
Yeah. So
Okay, I'm going to try. Okay, can you see the slides?
yes. Yeah, I can see the slides.
Oh, this is not working. Let's see what I really want to do. Is there a way for me to share the screen while seeing? I'm still just seeing your picture.
I mean, I can see the slides.
Right, but I want to see the audience.
Oh, I see. I have to put the. Let's see. Hmm.
Okay, we don't, if you can't figure it out, we don't have to do that.
Yeah, that's still a bit. Add participants.
Oh, I lost you.
Yeah, I think I don't know. Maybe I can check for later that how to show my video.
It's pretty easy. Usually you just click on the little video icon.
Yeah, I think I did that, but it doesn't work.
Okay.
Yeah, I think maybe you can start and maybe you try next time.
Okay.
Yeah.
Okay, can everybody hear me? Okay. So last time I started talking about simple decisions, chapter 16. For those of you who are just joining us today, I skipped chapter 15. And this is about utility. So remember from chapter 13 that utility theory plus probability theory gives us decision theory. That is, how do I decide what to do next? And we make decisions based on how much we prefer the states that we could get to and how likely it is that we're going to get to those states depending on our actions. So it's no longer, I'm getting a big echo. Are you, or maybe you could turn off your mic on your end, Hanchu?
Yes.
Okay, sounds good now,
Okay.
I think. Okay, so we've been dealing with worlds that are deterministic, where the results of our actions are known ahead of time, that if I do some action in some state, then I'm going to get to some next state. But now we're in a situation where, the world is not deterministic. I can't be sure that when I go to my car, it's going to be there and I'm going to be able to get home. So to reflect this uncertainty in the world, the next state is there's now a probability distribution over the next state. So there's a probability that the result of my action in state S0 is S prime. And this is a probability distribution, which means...
Hi, Gary.
Yeah.
I think you should share your slides. Seems we can only see the first slide.
Oh,
Yeah.
that's weird. Let me stop sharing. Hi, everyone. Okay, let's just share the entire screen. See how that goes.
Yeah.
Okay.
Yeah.
Is that
good.
fine?
Yeah.
Okay, good. I always like that.
Yes. Very good.
That's always so cool.
No. You should go to the previous.
Yeah, no, but I like to look at this. Okay.
Okay. Yeah. Okay.
Okay. So, right. So that's just the second slide. So you haven't really missed much. And so last time I talked about trying to get a date and the decision to act in a certain way, that is to ask for a date, is going to depend on my expected utility from that action. That is, it's the weighted sum over all the possible outcomes times the utility of those outcomes. And that gives me my expected utility. On average, how happy am I going to be if I do this action? So again, here's the formula. The expected utility of asking, that's an action in a state, depends on the probability of the result of that state, given that I take that action in that state, times the utility of that. So it's a weighted sum over my utilities. And again, it's expected because I don't know for sure what's going to happen. So that these are, and these have, the p's here have to sum to 1, right? So this is in a world where I assume I either get a date or I get rejected. And, since I'm in computer science, I'll probably get rejected. because I'm a nerd. So, okay, so this is the expected utility of performing the ask action given that I'm in state S0. So state S0 could be various states, like I'm feeling good, I'm very confident in myself, or I'm having a bad hair day. Those things are going to have different outcomes depending on the state, right? So, okay, so I think I've said all this. Now, this U up there, utility, or in the equation below in the middle, it's U of S prime, is a function that returns a single number that's the utility of state S. So there's no restrictions on what utility, what kind of number that could be. It could be 10, could be 1,000. It's just important that it is a ordering over my states that such that I prefer state S prime to state S. If I prefer state S prime to state S, then the utility of state S has to be bigger than the utility of state S prime. And what's remarkable about utility theory is that there are some axioms of utility theory that lead to a theorem that says there is such a function that actually maps states into numbers that reflect your preferences. I'm not going to prove that theorem, but I'm going to tell you about the axioms that lead to it. But anyway, right now, we've now done what we said we were going to do at the beginning of the course. We're going to define rational behavior as taking the action that maximizes my expected utility. So I have a variety of actions I could take in this state. I could keep talking to you, or I could just hang up, and that would have poor utility for me because I would get bad capes. Or you know, a variety of things I could do in this state. I could start singing, and then I'd get bad capes, etc. So I have usually I have a finite set of actions that I can take, discrete set, but a harder problem is if my actions are continuous. So, for example, I could be trying to control my car, right, which has a bunch of continuous things I can do. The accelerator has not a discrete set of actions with respect to the accelerator. It's how far I'm pushing it, and turning the wheel is also not discrete. It's a continuous set of actions. For our purposes, in order to make what I'm going to talk about tractable for this course, we're going to assume that both the states are discrete and the actions are discrete. So there's a finite set of states and a finite discrete set of actions. Okay, that's the setting we're going to be in. So today I'm going to talk about the axioms of utility theory, and that utility theory maps these preferences to numbers, and then talk a little bit about money. I'm not going to ask you for money, but I will accept donations. Okay. So this is our notation preferences. So this, notice it's not like a greater than or equal to sign. It's a funny greater than sign. And A prefers, the agent prefers A over B is what the first one means. The second one is that the agent is indifferent to A or B. And the third one is the agent prefers A or B over B, or is indifferent to them. So this is, you know, a new kind of space where we have some sort of metric. It's not exactly a metric, but There are at least preference relationships. So oddly enough, what utility theory talks about is often lotteries. So you measure how much you would like a prize versus a lottery, which is an uncertain prize. So a lottery L is this thing in these brackets. What this means is with probability P, the outcome will be A, and with probability 1 minus P, the outcome will be B. And it doesn't have to be just two things, or it could be three things, or they could be nested. So the second item here could be another lottery. Okay. And so the main issue for utility theory is to understand how preferences between complex lotteries are related to preferences between the underlying states in those lotteries. So I'm going to talk about the axioms. So there are 6 axioms of utility theory. Excuse me. The first one is orderability. So given any two lotteries, you can't not play the game. You have to prefer one to the other or rate the two as equally preferable, or so exactly one of A is preferred to B, B is preferred to A, or A, I'm indifferent. Transitivity is just what you'd expect. If an agent prefers A to B and they prefer B to C, then they have to prefer A to C. So those are the first two. You have to have preferences between two states, and they have to be transitive. The third one is continuity. And this is, so if there's some lottery between A and C in preference, so, and you can, again, you can think of these lotteries as states, because you could have a lottery where there's only one outcome and the probability is 1, for example. But if B is between A and C in preference, so C could be, I get the date, A could be I rejected, and B is, let me think about it. That's better than being rejected. It's not quite as good as getting the date. So there should be some probability P for which a rational agent will be indifferent between getting B for sure and the lottery that yields A with probability P and C with probability 1 minus P. So what this says is, so B is, let me think about it. I should be agnostic or indifferent between that and, say, I forgot which one I said was which, but let's say, I think I said C was getting the date. Let's say A is getting the date. I might be, I might be just as happy to find out that he or she will think about it versus, say, I don't know, 0.8 of getting the date and 0.2 of being rejected, or maybe 0.4 of getting the date and 0.6 of getting rejected. I think I'd rather get the answer that the person would think about it than having a higher likelihood of being rejected. Okay? Does that make sense? Are they shaking their heads yes? Panchu?
Yes. So I
Okay.
say yes.
Okay. Okay, so we're up to, we've had 1, 2, 3. Here's the fourth one. Substitutability. This is, so if I'm indifferent between A and B, and let's just think of A and B as states, but they can be lotteries, right? Then the agent is indifferent between two more complex lotteries that are the same, except that B is substituted for A in one of them. So basically this says if A equals B in utility, then having the probability P of getting A and 1 minus P of getting C should be, I should be indifferent between that and the probability P of getting B instead and 1 minus P getting C. Okay, so if A and B are equivalent, I should be able to substitute B for A in any kind of lottery like this. Make sense? Okay. Okay, we're up to 5, monotonicity. If two lotteries have the same two possible outcomes, A and B, and I prefer A to B, then I have to prefer the lottery that has a higher probability for A, and vice versa. This is, it looks complicated, but basically it's very intuitive, right? So if I prefer A to B, then if P is greater than Q, and these are probabilities, then I should prefer a lottery where the probability of P of getting A is bigger than the probability of Q of getting A. Right? So if I like getting the date versus getting rejected, then I should prefer a lottery where I'm more likely to get the date. No big surprises there. This is intuitively obvious to the most casual observer. Okay, and then this is the last one. It's a little more complicated. It's called the no fun in gambling axiom. So the idea is if I have if I have a lottery where I have a probability P of getting A and a probability of 1 minus P of getting the second lottery where it's probability Q of getting B and 1 minus Q of getting C, using the laws of probability, that's equivalent to a 3-outcome lottery, where I just multiply 1 minus P times the probability in that second lottery. So 1 minus P times Q, and then 1 minus P times 1 minus Q. This is the same outcome. But the difference is I don't get to play 2 lotteries. I don't get to gamble twice. I just gamble once for the same outcome. There's no difference in the probabilities here. That's just using probability theory to get this. So now, so does that make sense? Why it's no fun in gambling? See, it means that you just gamble once instead of gambling twice. You can fix that, of course, by creating a, well, let's see. I don't know if you can fix it. You have to create some sort of utility where you prefer to get to gamble more than once somehow. Okay. So one thing to note here is that the second thing here, can you see my mouse? Do you see my mouse?
Yes.
Okay. So this is a lottery with 3 outcomes. First one, second one, third one, as opposed to one with 2 outcomes. and then the second outcome is another lottery. So just to make that point. So this is another picture of the same thing. So with P, probability P, I get A, 1 minus P, I have another lottery with a probability Q of getting B and a probability 1 minus Q of getting C. If I just multiply these things together, I get the same outcomes, same probabilities, but it's only one lottery. Okay. So those are the 6 axioms of utility, and they make sense because it's like the axioms of probability. Remember, we had that thing where if somebody violated the axioms of probability so that they thought the probability of A or B was different than the probability of, or the probability of A and B was not just the probability of A. Let's see, I'm blanking on what it is. Okay, but you know what I'm saying. We had that idea where if you violated the axioms of probability, I could always win bets with you. And it's the same thing here. So here's the simplest example of this. Suppose you violate transitivity. So you prefer A to B, and you prefer C to A, and you prefer B to C. Then you've got this weird thing where things are going in a circle. And what this graph is showing is if I'm in B and I prefer A to B, if I pay a penny, I would like to pay a penny to get to state A, say. I'm just making up this number. So you'll pay 1 cent to get from B to A, then you'll pay a cent to get from A to C, and then you'll pay a cent to get from C to B. So I can just keep collecting money from you, and you'll go around and around in the circle. So the cool thing about all this is that these 6 axioms, lead to a theorem. And notice who's on this theorem. This guy should look familiar. Von Neumann. Your laptops are von Neumann machines. So von Neumann did more than think up what a computer should look like. So they proved that given preferences satisfying these axioms, then there exists a real valued function u such that u of A is greater than or equal to the utility of B if and only if my preference for A, either I prefer A to B or I'm indifferent between A and B. And that also leads to the utility of this lottery. Notice there's no u's inside here, they're just states, is equal to the sum of the probabilities of each state times the utility of that state. So this equation down here relates lotteries and utilities in such a way that this is how I that non-trivial, I would say. Okay. So then the question is, if utilities map states to real numbers, what are the numbers? And there's a procedure that to assign numbers to utilities. A to some lottery that has size. probability, worst possible catastrophe, you bottom, probability 1 minus p, and you adjust the lottery probability until you're indifferent between A and the lottery. So here's a question. What value to you is playing a lottery in which one outcome you live and the other you die with 1/1,000,000th probability? Okay. Generally, I mean, this still has a negative value for me. Maybe if it was 1 billion, I'd be okay with it. But this is a micromort. This is a unit of, you know, your fear of death, basically. So a micromort is a unit of risk measuring a 1 in a million probability of death. And it comes from micro, meaning 1/1,000,000th, and mortality, death. And then these can be used to measure the riskiness of various day-to-day activities. Here's a bunch of activities that increase your risk of death by roughly 1 micromort, and their associated cause of death. So traveling 6 miles by motorbike is about 1 micromort in riskiness. Traveling 17 miles by walking, so these are equivalent. All of these are equivalent in risk assessment. 17 miles by walking, 6 miles by motorbike, 10 miles by bicycle, 230 miles by car, 1,000 miles by jet, 6,000 miles by train. So what are you going to do? You want to take a train. Although you can go 12,000 miles if you stay within the United States. Okay, but flying around the world in general by jet is you reduce your, it's 12 times more risky, roughly, to travel by jet around the world than it is to travel by jet within the United States. On the other hand, hang gliding is 8 micromorts per trip, so please stay away from the Torrey Pines glider port and don't go to raves, okay, because ecstasy is half a micromort per tablet. Okay. Got that?
Yeah.
Don't take ecstasy. So 2 gives you a whole micromort. So taking 2 tabs of ecstasy is equivalent to traveling 6 miles by motorcycle. Okay, money. What about money? So a lot of times people compute something called the expected monetary value. So this is a lot like utility. So, you know, I could flip a coin and give you $10 if it comes out heads, and $0 if it comes out tails. And if it's a fair coin, then those two outcomes are 50-50. My expected monetary value, though, is $5. Okay, that's not, but would you pay $5 to do that? That's essentially what that means. That's how is your utility for that outcome? Would you pay $5 to either lose that $5 or get $10? That's the question. So those are two kind of states where the one state is you pay $5 and you get $0, and the other outcome of the lottery is you pay $5 and you get $10. Would you take that bet? Well, think about it if it was $50. would you pay $50 to maybe lose that $50 or to get $100? Those are equivalent in monetary value, but I wouldn't pay $50 to find out whether or not I'm going to get $100. My utility for money is different than money. So, for example, if you think about $100, I think somebody computed once that it wasn't worth Bill Gates' time to drop down, to lean down and pick up a $10,000 bill. I don't know if that's probably just somebody made that up. But if I'm homeless and you give me $100, that is much more utility for me than giving $100 to Bill Gates. He probably doesn't care if you give him $100. Doesn't change his utility of his state without the $100 and his state with the $100 is probably about the same. Very close anyway. Hardly noticeable difference. So here's a utility curve for money. This is a typical one where so it's if the utility for money was equal to the expected monetary value, this would be a straight line. But it's not a straight line. If I have $800,000, my utility for having $800,000 when I already have $700,000 is not much higher. But if I have, and my utility for having, I don't know what that is, maybe $10 is 0, but getting $100 goes up a lot, you know, etc. Over here, this is the negative side. So this is a person who is very unhappy when they don't have, I don't know what the scale is here, like $25,000, but is even more unhappy if they have $50,000. In this case, it's almost a straight line, so it's about, it goes down with double the money, it would go down twice as much. Okay, so that's a normal person. But a person who's addicted to gambling might have a utility curve like this. So losing, you know, if I'm in debt by $100,000, taking a bet that in which I might afterwards owe $200,000, well, this is a decelerating curve here, right? I could like that as much as you know, having no debt. So if I had like a 50-50 chance of losing $100,000 when I'm already $100,000 in debt versus not owing anything, then I might take that bet because I'm risk seeking. So hopefully you are all like this and not like this. Okay, so this is looking like it's going to be a very short lecture, so I might pull up another set of slides here. So in summary, probability theory describes what an agent should believe on the basis of evidence, where utility theory describes what an agent wants, and then a decision theory puts the two together to describe what an agent ought to do. And so a rational agent then is one that out of all the actions in a situation chooses the one that maximizes his or her expected utility. And so you can figure out what people's utilities are by figuring out, you know, you can figure out points on this curve basically by saying, well, if you had $100,000, what kind of bet would you take to get $200,000 versus lose that money. So what's your utility for that bet? And then you can figure out from that what the height of this curve is. And that's something we should do in class sometime, but I'm not there to see you, so can't get you to bet. Okay, and so we can use this theory to build a system that makes decisions by considering all possible actions and choosing the one that leads to the best expected outcome. And so this is something that's going to lead us into Markov decision processes and reinforcement learning, which is a really cool thing because reinforcement learning is the best attested thing about the brain that we know about learning. That is, we know where in your brain your action system is, and we can tell there are parts of your brain that light up for different values of things. So we have a fairly well worked out mapping of the brain to various elements of decision making and reinforcement learning. Okay, and then an agent whose preferences are consistent with these 6 axioms can be described as having a utility function that maps states to numbers that are ordered in the same way as its preferences, and you shouldn't confuse money with utility. Okay. Let me see. We still have 12 minutes. Let me see if I can pull something else up to talk about. Where is chapter 17 in PowerPoint form? Okay, so that was a description of how to make a decision. One decision at one point in time. What about things where you have to make a sequence of decisions? Those are called Markov decision processes. And POMDPs are like life. So POMDPs are partially observable Markov decision processes. You remember in the lectures on belief nets and using Gibbs sampling, going through from state to state to state was a Markov process, and we knew what the states were. In POMDPs, that's how you pronounce that, you can't actually know what state you're in. Instead, you have a belief about what your state you're in. You have a probability distribution over the states. All you know is that given a state, you get an observation with some probability. And so you don't really know what state you're in. You know, if I was in a certain state, I'd expect to get a certain observation, but I don't know. I could get the same observation from other states. So in fact, the states are hidden to you. And that's basically life, right? So I lecture to you, I look at your face, it looks like you understand what I'm saying, and so that's a partially observable state. I don't really know that you understand what I'm saying, and I don't find out until the midterm that in fact you have no idea what I'm saying. So that was supposed to be a joke. Okay, so a lot of problems require sequential decisions like state space search, chess, video games, life, both real and the game of. And in this chapter, we consider sequential decisions where actions have uncertain outcomes, states have rewards, and those rewards are related to our utility. So we're trying to maximize our long-term expected rewards. And we're going to consider the special case of Markov decision process problems. So MDPs, so you know what a Markov chain is now. An MDP is a sequential decision problem defined by having a finite, discrete set of states. That's the Markov, part of what a Markov process is. It has a discrete set of states. Some reward function that is the reward I get in some state, like I get the date or I get punishment, and a set of actions. Sometimes written this way to mean A of S is a set of actions I can take in state S. And then I have a transition function, which is the probability that, this notation is kind of screwed up. Let's read this one. This is the probability of getting to state S prime. This should be SAS prime over here. The probability of getting to state S prime, given that I'm in state S and I take action A. So this becomes, this is slightly different than a Markov chain because I get to act. The Markov chain, I'm in some state and I have a probability distribution over the next states. Now, I'm in some state and I get to take an action that leads to a probability distribution over the next states. Okay, that's a slight but very important difference. So this is the picture you should have in your head of what's going on. So I'm an agent. I take some action that affects the environment. And from that, I get a reward, and I get to a new state. And then, given the state I'm in and the reward, I decide on another action. So everything here is discrete. So time is discrete. I get to take one action per step. The actions are discrete. The rewards are some number, could be any numbers. In fact, the rewards could be negative. So that having a negative reward, it could be that every step I take, I get a little shock until I get to someplace that's my goal. And so getting a little shock every time step tends to encourage me to find a quick get out of this situation as quickly as possible. So actually having negative rewards can be useful if you want your agent to behave in a very efficient manner. Okay, and so this is the picture. I'm in state ST, take action A, I get reward T plus 1, and I get to state T plus 1. So one thing about this is completely observable. I know what state I'm in. And getting from here to here is based on this this transition function that gives me a probability distribution over next states given that I'm in this state and I take this action. This is what actually happens to me. I have these S, A, R, S, A, and in fact, one of the learning rules for reinforcement learning is called SARSA. And notice we got S-A-R-S-A, SARSA. I'm not going to tell you about SARSA, but interesting to know. Okay. Here's a standard example MDP that you will get in any AI course where you hear about MDPs. It's called Grid World. And the agent starts down here in this lower left corner. And the agent always knows what state they're in. So this would be state 2, 1, state 3, 1, state 3, 2, etc. And I want to get here. This is heaven. I get a +1 reward. And all the rewards in here is 0. And this is hell. I get a -1 reward. And my goal is to get to heaven and not to hell. Right? That if I get here, if I take some actions, a sequence of actions that get me to here, I'm going to maximize my long-term expected utility. If I have little foot shocks in here, like -0.1 or -0.01 or something like that, then I will want to get to this goal as quickly as possible. Okay, so by setting the problem up so there are little foot shocks here, I'll get an more efficient agent, perhaps. Yeah, so here's the foot shocks, -0.04. The trick is, though, that as I was saying, my actions are stochastic. That is, if I try to move up, I go up with probability 0.8, but I'll move left or right with probability 0.1. So my actions are stochastic. In particular, this is going to make a big difference in this state 3, 2. If obviously what I want to do in this state is go up, but if I have a 10% chance of going to hell doing that, I'm going to want to probably avoid actually ever being in this state. So in that situation, the optimal thing to do will be to try to go up here and right. And depending on these little foot shocks and stuff, they may be big enough that I don't care. I want to get out of here as soon as possible. But typically, depending on this foot shock amount, if I go here to state 2, 1, I'll tend to want to go back and go over here so that I avoid ever going to hell. Okay? And if I'm here and I go up, I'll have a 10% chance of staying here, because if I hit a wall, I just stay in the state I'm in. So that's the situation. And I'm waiting for my watch to come back. 11:49. Got 1 minute. Okay. And so the transitions are Markovian. They only depend on the current state, not the sequence of states that got you here. So that's the Markov property. The probability of the next state only depends on the current state and the action that you take. Okay? Unlike real life, where you never stop paying for your past. Okay. So that's the situation. What we're going to do next time on Monday is we're going to figure out what's the optimal thing to do here in order to optimize my long-term expected reward or utility. Okay.
Okay, thanks, Gary.
See you on Monday. Or not.
All right.
Bye.
So I will finish now.
Okay.
Hey, do you know when he's gonna release the PhD grades?
At the end of this week, maybe on Saturday or Sunday.
Okay, and also, do you know if he's like actually keeping track of the iClicker?
I'm sorry.
Do you know if he's actually keeping track of the iClicker scores?
The iClicker score. I think Gary will deal with that. Yeah.
Okay.
Yeah, but he still have to figure it out because the TS has no access to iClicker. That's only the professor who does.
Okay, is it possible that I can know my score?
I don't know. You should just ask Gary, but I don't know. Sorry.
I just had a quick question on the timing of my PA.
Okay.
I'm not very sure whether or not